Hi, my name is Ghadir Abouda. I'm going to present our paper with title Accelerating Entity Lookups in Knowledge Graphs Through Embeddings. This work is in collaboration with both Sara Vinan and Ashraf from Qatar Computing Research Institute in Hamad bin Khalifa University. So let's start. Knowledge graph is a semantic knowledge base that integrates factual knowledge from a wide range of domains into a single graph, a graph that consists of a set of entities or nodes and the relationships between them. This graph is usually presented as a set of triples, like Doha, capital of Qatar. Knowledge graphs bring potent solutions for many tasks. One of these tasks is semantic augmentation. It is the task of adding semantics to tabular data. Tabular data, such as CSVs, relational database, or spreadsheets, is the most common format in the web and the enterprise data lakes. However, the usage of tabular data is often limited by many data quality issues, such as incomplete or missing data. Semantic augmentation uses knowledge graph as a semantic reference for entities in the tabular data. This requires learning the correspondence between records in the tabular entities and the entities in the knowledge graph. Semantically enriching the table components, such as cells, rows, and columns, with the semantics brought from external knowledge graph can add a practical value to different tasks, such as entity disambiguation, error detection and repair in tabular data, and many other applications, especially in enterprise data lakes. The first step for all these applications is the lookup function, which matches a query string to a set of candidate entities from the knowledge graph. For example, if we have this table and we want to search for the string query cork in a knowledge graph like Wikidata, the lookup function retrieves a set of entities that matches the query string, such as cork as a city or cork as a material derived from the cork. The lookup function doesn't necessarily match the string query precisely with relevant entities. It's possible that the query string has misspelling or abbreviation. So for example, searching for College Cork instead of University College Cork. Once the candidate set of entities is retrieved by the lookup function, the entities can be processed further based on the application-specific manner. For example, these entities can be used to identify a type for certain column in the table. In this example, this column can be identified with RDF class type university from JPedia, for instance. Another example or another task could be by annotating certain cells in the table with entities in the knowledge graph. Like, for example, mapping Utrecht network to Utrecht in knowledge graph. Current approaches to implement the lookup function can be done by using remote lookup services such as Wikidata or JPedia APIs. Another approach could be by indexing the entity titles and use that index for searching. Another approach could be by implementing a custom similarity metric from scratch or use fuzzy matching libraries. Unfortunately, none of these approaches are optimized to support different similarity metrics or tolerant to data cleanness problems. They don't support bulk lookup. So in one of the systems we tested for semantic table annotation, it requires 3 days to match tables to entities in the knowledge graph. They also don't support semantic similarity. So for example, if we search for Dutchland in the knowledge graph, the lookup function should retrieve Germany, even though the Dutchland is not an entity in the knowledge graph, but an alias. To address these problems, we propose mlookup, a novel approach for lookup operation. It represents entities in knowledge graph in a compact vector representation that supports faster lookup. It trains an embedding model on the entities in the knowledge graph and create an index of these embedding that is more space efficient and faster than current lookup operations. mlookup is not a typical knowledge graph embedding. Our approach is trained on the symbolic representation of entities in the knowledge graph. As a lookup function, it will accept a string, but it will retrieve a set of semantic and syntactic similar entities from the knowledge graph. We will go through all these details shortly. Instead of optimizing for individual similarity metrics such as edit distance, our framework trains a deep learning model to learn a generic similarity metric in an unsupervised manner. It can handle both syntactic and semantic similarities, and it can be used in different semantic annotation tasks. It supports a bulk query and create an index of embeddings and use it for the search. So we start from the knowledge graph, we learn an embedding model, we generate embeddings for the entities in the knowledge graph, and then compress these entities and produce an index and use this index efficiently to support semantic and syntactic lookup queries. The first step of implementing mLookup is to extract different entity string mentions for each entity in the knowledge graph. String mentions are labels and aliases that can be extracted from different properties, such as RDFS label. The string mention can be a single word or multiple words. We use character-based one-hot encoding to convert each string into a matrix of A by L, where A is the alphabet of the entity mentions and L is the length of the longest entity mention. Each column of this matrix stores a one-hot encoding for each character in the string mention. This matrix is the input for the embedding learner. Most of the lookup functions operate on the string representation of entities. This representation is not applicable to different scenarios, such as abbreviation or aliases. We propose to transform entity mention into a different representation that encodes semantic and syntactic similarity. We empirically found that using a single embedding model that subsumes both similarities is less accurate than using two separate models. So we use convolutional neural network for learning embedding that estimates the syntactic similarity. This is inspired by the literature that the output of the CNN model with max falling over two strings preserve the bounds of edit distance. For the semantic similarity, we train fast text to capture the similarity between the entities and their synonyms. Finally, we aggregate the output of the two models using two linear layers with ReLU activation and produce a single 64-dimensional embedding vector. mLookup uses two models to transform a string mention into an embedding. We need a loss function to train these models. We use the triplet loss function that encodes syntactic and semantic similarity. mLookup is trained on triplet embedding in the form of anchor, positive, negative. The loss function ensures that the distance between the embedding of an anchor and the negative is larger than the distance between the embedding of the anchor and the positive. So for example, the distance between the embedding of Cork and Dublin should be smaller than the distance between Cork and Microsoft. The core of the training process is generating a triplet examples that encode the similarity and use them to train the model. The process of the triplet mining or generation involves collecting a set of triplets in the form of anchor, positive, negative. For each entity, the positive example is one of the entity synonyms that can be extracted by different properties, such as RDFS label. For the negative example, it is one of the labels of randomly chosen entities that are unlikely related to the entity. For example, if we have entity Germany, these are possible triplets that we can generate for entity Germany. So Germany, Federal Republic of Germany is the label or a synonym, and Bill Gates is a label of a random entity that's not related to Germany. During the training, the model is updated based on the minimum of the triplet loss and backpropagate that to improve the embedding models. Once the embedding model is learned, we generate an embedding for each entity. We produce a matrix where each row corresponds to an entity embedding of 64-dimensional vector. We need to use this matrix for similarity search. For instance, given a lookup query, we want the lookup function to retrieve the set of k entities from the matrix whose embeddings are nearest to Q. The question here is, how can we efficiently search the embedding matrix to find the most similar embeddings to Q? To speed up the search process, we consider approximate representation of the embeddings. We use the product quantization to compress the entity embeddings to reduce the storage and ensures faster retrieval. The compression component is an optional step in mLookup. Any appropriate compression mechanism can be used based on their accuracy, storage, and latency trade-off. Product quantization compress the embeddings by slicing each embedding vector into subvectors, and then run k-means clustering on the small vectors, then replace each vector with the closest centroid, resulting into a limited approximation. We can search this representation efficiently without actually decompressing the vectors using the centered IDs of the clusters. So mLookup trains on a symbolic representation of the knowledge graph on the set of triplets that generated for each entity in the form of anchor, positive, negative. The embedding learner in mLookup is a two-model approach that encodes both syntactic and semantic similarity. And finally, we use the product quantization mechanism to compress and index the embeddings so we can efficiently search them and serve syntactic and semantic lookup queries. In the experiment, we test the acceleration of mLookup in different application scenarios. For the datasets, we use the SimTab challenge datasets, which is a challenge for benchmarking systems for matching tabular data with knowledge graphs. We use the SimTab challenge datasets of 2020 and 2019, and for the knowledge graph, Wikidata, and Dpedia. For the applications, we consider 4 different application scenarios. Cell entity annotation that annotate a cell in a table with an entity from the knowledge graph, column type annotation that annotate a column with a type from the knowledge graph, and that entity disambiguation identify the correct entity that is referred to by a query. And for data reveal is replace some of the missing values in a table row using knowledge graph. We consider the best of these systems or the state-of-the-art system for each task and replace mLookup with the lookup operation inside these systems. We demonstrate the speedup of mLookup over the baselines and evaluate the accuracy by F-score. In this experiment, we test the speedup of mLookup in different systems for different tasks. For cell entity annotation and column type annotation, we choose the system of the winners in the SimTab challenge. For entity disambiguation and data repair, we choose the state-of-the-art system. And here, I'm showing a small set of these systems, and the remaining can be found in the paper. For each system, we replace the lookup function by the mLookup. We measure the time taken by the original lookup function and that by mLookup and report the speedup ratio. We consider 2 variants of mLookup. The numbers in the red columns are the speedup for mLookup implementation with compression, and the numbers in the green columns are for mLookup without compression. From this experiment, we can see that mLookup can achieve order of magnitude of speedup and further speedup when the GPU is available. For the same set of tasks and the same system, in this experiment, we test the accuracy before and after replacing the lookup in this system with mLookup. The red column is the F-score when we replace the lookup function with mLookup implementation with compression. And the one in the green is the F-score of mLookup without the compression. The column in blue is the F-score of the system before replacing the lookup function. The experiment shows that the mLookup can speed the lookup operation with almost no reduction in accuracy. In this experiment, we compare mLookup with different remote and local services. We compare mLookup with different approaches that are widely used in semantic annotation tasks. Here, I'm showing a small set of these examples, and the remaining can be found in the paper. Both mLookup and the baselines are provided with the same set of queries and retrieves the top 10 relevant entities. The query is considered successful if the correct entity is retrieved in the top 10 entities. We report the speedup and the F-score of mLookup over baselines. And again, as we can see from the experiments, mLookup combines all these services in accuracy with faster retrieval. In this experiment, we investigate how the performance of mLookup would be impacted by noisy dataset. For the same set of tasks and the same set of systems and for the same knowledge graph, in this case Wikipedia, we tested the performance of mLookup and the systems on synthetically created noisy dataset. We introduce errors into 10% of the cells by dropping some or inserting some letters, transpose some letters, swap tokens, and so on. The performance of all the systems with the original lookup function has dropped, as we can see in the blue column. However, mLookup shows substantially better accuracy than these systems, especially in the presence of errors. mLookup train embedding models on the string representation of entities instead of using pre-trained models. Moreover, we train a CNN-based model rather than using an NLP-based model. In this experiment, we evaluate these design choices by varying the embedding model algorithms and evaluate the F-score for cell entity annotation task. We test the performance of mLookup and different learning embedding models on the original dataset and the created noisy dataset. We used pre-trained models for fast text, BERT, and word-to-vec. We also used an trained NLSTM model over the labels analysis of knowledge graph entities. As we can see from the table, mLookup outperforms all of these popular embedding learning algorithms, especially in the presence of errors. In conclusion, mLookup is not a new knowledge graph embedding algorithm, nor it is a new algorithm for annotation task. It optimizes the lookup function, which is a main building block for many applications. mLookup provides order of magnitude speedup in different applications, and it's also robust for the many data cleanness problems. mLookup is an open source project and can be found in this GitHub repository. For more details about the sensitivity analysis and other experiments, please refer to the paper for details. Thank you.